All right, to bring this session home, we have our fourth and final presentation. This presentation is going to be presented by Cosmin Ticleanu, and Cosmin is coming to us from the BRE's Building Technology Group, where Cosmin has an extensive amount of experience doing daylighting and lighting consulting, and today we'll be presenting Assessing Daylight Provision Calculations in EN 17037. Welcome, Cosmin.
Thank you, Kevin, for the introduction, and thank you, VELUX, for the opportunity to take part in the Daylight Symposium. Yes, in the next minutes, I'm going to present some preliminary findings of a research project that we are currently working on regarding the daylight provision calculation methods in the European standard for daylighting buildings. But first, let's have a quick look at the background of this project. I'm sure we all know, and we also tried to capture this in a comprehensive report on lighting and health that we did a few years ago. There is extensive research showing the benefits of daylight, which go beyond visual and cognitive to health and well-being, with also overall positive impacts on work and performance. So it is vital for workplaces and homes to have good levels of daylight. Over the years, various standards, guidelines, and environmental schemes have been produced that address daylight provision in buildings. Some focus specifically on this, on daylight, for example, the now withdrawn British standard BS 8206 Part 2, or our BRE report site layout planning for daylight and sunlight, which is widely used by local authorities during planning permission to determine the impacts of new developments and ensure good access to daylight and sunlight, both new and existing buildings. At the moment, we are updating our report to reflect the latest standard recommendations on daylight provision in new buildings. Other schemes have daylight as one of various other environmental aspects, such as our BREEAM standard, as well as LEED, WELL, and others. Since 2019, we have this EN 17037 as the European standard for daylighting buildings. It addresses both daylight provision as well as other important aspects, exposure to sunlight, view out, and glare. But in terms of daylight provision, which is the focus of our project, it proposes two methods. One predicts illuminances over a typical year on a grid of points in each room using weather data. And there are illuminance benchmarks that differ between vertical windows and horizontal roof lights, as well as for different levels of recommendation. But generally, these targets are 100, 300, 500, and 750 lux across half or across 95% of the space over half of the annual daylight hours. The other method, which is simpler, predicts overcast sky daylight factors. The target daylight factors are determined for each location from the target illuminances, and the median external horizontal illuminances, which are basically measures of cumulative daylight availability at that specific location. And these tables here on the screen show you the target values for London as an example. There is also a UK national annex to the standard that gives specific target levels for dwellings in the UK, which are lower than the target values in the main standard. These are intended for hard-to-light dwellings, for example, in basements or with significant external obstructions or with tall trees outside, or for existing buildings being refurbished or converted into dwellings. The new standard has more complex methodologies than before in terms of calculating daylight provision in buildings, but it doesn't fully explain how to carry out these calculations. It's unclear, for instance, whether the two methods give similar results, whether the one makes it easier to achieve the recommendations. So this is what we are trying to investigate in our current research project. We set up this project, which is funded by CIPSI, because there are various issues around daylight calculations. Firstly, software tools normally use the radiance calculation engine, which has input parameters that control the precision of modeling, but also the time taken. Software tools are ends to radians and may set parameters or require users to input them. And in practice, different runs may give significantly different results. The use of weather data is an additional issue. Weather data files rarely reflect daylight as the most important parameter and occasionally may lead to anomalous results. For example, during the preparation of the UK national annex to EN 17037, London was predicted to have less daylight than Belfast, which is further north and with a cloudier climate. Other issues can arise from how the calculation grid is set up. For example, can parts of the room, like corridors or alcoves, be ignored? Or how does the grid size affect accuracy in rooms with multiple windows? Is a standard half a meter offset from the walls appropriate in smaller rooms? Without clear guidance and recommendations, users can improve the results by tweaking parameters, choosing inappropriate weather data, or omitting darker parts of the room. And so the aim of our research is to investigate the daylight provision calculation methods in EN 17037 to provide detailed guidance for daylighting practitioners on applying this in practice. The project is based on computer modeling of daylight in a variety of room shapes and sizes with different external obstructions as occurring in real-world situations. It addresses differences in calculation results arising from the choice of the calculation method, i.e. daylight illuminance-based or daylight factor-based. The setup of calculation grids, including grid location, size and offset from the walls, ground plane size and computational parameters, as well as the selection of weather data. At the end of the project, we are hoping to provide guidance for daylighting practitioners and disseminate the results in a detailed technical report and, if appropriate, in a journal article. This is how we set up the project. Informed by findings from a workshop we held with daylight experts earlier this year and a literature review, we planned a first study on the optimal set of radiance parameters to use for the main study. Also a second study on the size of the ground plane, a third study on the impacts of the calculation grids, and the fourth study to identify suitable weather data sets to use for climate-based daylight modeling. Informed by the outcomes of these four studies, the main study consists of calculating daylight factor and daylight autonomy for different target illuminances to determine whether the two different methods in EN 17037 give comparable results. These are room layouts that we have chosen so far. There are typical layouts for apartments and townhouses, together with larger multi-windowed spaces typical of office interiors. The rooms were chosen with windows on one or more walls, as well as with roof lights. And room dimensions vary from 2 by 3 meters for kitchens to 3 by 4 meters for bedrooms to 4 by 7 meters for living rooms to 8 by 20 meters for offices. A range of external obstructions of different shapes and sizes, up to 50 meters in high, were placed at various distances opposite and to the side of the rooms, including balconies for residential living rooms and shading louvers for offices. And there are also rooms without obstructions. Next, I'm going to present key findings of the first study on radiance parameters. For this study, we used 3 residential rooms, namely a combined living and kitchen lit from one side, room type R5, but also from a roof light above the kitchen, room type R7, as well as a bedroom, room type R1. These rooms were placed at a selection of 5 locations throughout the building. We also used an office with 1 fully glazed facade, room type R9, as well as an office with 2 adjacent fully glazed facades, room type R10. In the next slide. Okay. We calculated daylight factor and daylight autonomy for 100, 300, 500, and 750 lux. using Diva for Rhino, which embeds the DACIM algorithm, and using 0.3 meter calculation grids at 0.85 meters above the floor, with a 0.3 meter wall offset in residential rooms and half a meter wall offset in offices. In all models, the ground plane was as large as the biggest object, which was a 1,000 meter long linear obstruction. And we used the Energy Plus weather file for London and typical double glazing and surface reflectances. After reviewing various papers by different authors on this topic, and also the radiance parameters used by several commercial available software tools, which we believe are commonly used by daylight prediction,ers, and after undertaking our own preliminary analysis, we chose these 5 sets of radiance parameters to use in Diva for Rhino. Set 1 was considered to be the top benchmark, above which a plateau was reached, and there were no variations between multiple runs, whereas the other sets were taken as still providing accurate results that did not depart significantly from the top benchmark, but within a shorter calculation time. And that actually applies to set 2, 3, and 4. We did statistical analysis of daylight factor and daylight autonomy results to establish if there were statistically significant differences between multiple runs of the same set of settings and between the different sets of settings. We started the analysis with room type R5, the combined living and kitchen lit from one side. Despite lowering the settings from set 1 through to set 4, we found no statistically significant differences in the results obtained using set 4 and any of sets 2, 3, and 4. However, the calculation time decreased substantially. There were statistically significant differences between the results obtained using any of sets 1 to 4 and set 5. This was the case for both daylight factor and daylight autonomy. As such, we hypothesized that using set 4 would be an appropriate way that can still provide accurate results, but within a more reasonable calculation time. We then verified this hypothesis for the other room types, R1, R7, R9, and R10. And overall, we found no statistically significant differences with set 4 between 4 different runs, nor between set 4 and set 2 for all other rooms. Hence, we concluded that using this set of radius parameters that you can see on the screen can provide accurate results within a reasonable calculation time. Next, we did the second study on the size of the ground plane. In part A, we varied ground plane size in multiples of window head height in the direction of the window without obstructions and kept the same size in the other directions. This was the case for room types R1, R5, and R9, namely bedroom, side-lit living kitchen, and office lit from one side. In part B, we varied ground plane size in all directions to also vary the size of the largest object in the model. This is because radiance calculation accuracy changes with S-mean, the minimum separation for cached irradiances, or in other words, the distance used for ambient interpolation, which in turn depends on Dmax, which is the largest dimension in the model, as well as the values for ambient accuracy and ambient resolution. So we varied the largest dimension in the model from 250 meters to 4,000 meters, and the value for ambient resolution from 128 to 2048 to obtain this range of S-mean from 0.04 to 0.63 meters. Ambient accuracy was kept constant to 0.01. It should also be noted that Diva automatically includes an infinite ground source in its calculations. This is meant to correct for the light that radiance sees as coming from the sky on the other side of the Earth if there is no ground in place. In this study, we found slightly different results for daylight factor and daylight autonomy. Daylight factor results did not vary with the ground plane size in the direction of the window without obstructions, but we found statistically significant differences for larger S-mean values, namely 0.31 and 0.63 meters. We also looked at calculation grid sizes and found no impact. For lower values of S-mean, we noted that the results of multiple runs were consistent and generally daylight factor values tending to be higher for larger S-mean values. Overall, we concluded that the ground plane does not need to be larger than the largest object in the model, but also that it would be more accurate to keep S-mean to no more than 0.16 meters. As for daylight autonomy, these results were different to the daylight factor calculations in that there were also statistically significant differences between ground plane sizes in the direction of the window without obstructions. And generally, a larger ground plane helped to increase spatial daylight autonomy in the room without obstructions, which faced west in our calculations. And so we believe that with a larger ground plane in place, this room received more ground reflected light in the afternoon. Currently, we are at the stage of undertaking the third study on the calculation grid. We are calculating daylight factor and daylight autonomy in several domestic rooms and an office space, using a range of calculation grids spaced from 0.1 meters to the maximum grid spacing allowed by the equation in the standard, and without and with a wall offset of 0.3 and 0.5 meters. These are some preliminary findings on the daylight factor results. These graphs show median daylight factors for each room assessed in the different scenarios. Whilst there isn't much variation in median daylight factors in some cases, there are cases where statistical analysis found significant differences between wall offset scenarios for the same grid sizes, as well as between grid sizes for the same wall offset scenarios. Generally, 0.1 meter grids, and on some occasions 0.3 meter grids, led to statistically significant differences. A half a meter wall offset also tended to cause statistically significant differences compared to 0.1 and 0.3. And overall, there were slightly higher results for a larger grid spacing and the wider wall offset. And looking at the findings to date, for accurate results, fine grids, namely 0.1 meter as a common denominator, and narrow wall offsets may be recommended. But then other questions arise. Should the wall offset be proportional to room dimensions, for example, as suggested in this year's release of EN 12464 Part 1 for grids to calculate or measure artificial lighting? Also, should the wall offset be related to the type of the room? For example, in an office, a bigger wall offset is logical compared to, say, a domestic kitchen with worktops around the walls. There are some initial conclusions that can be drawn from our study so far. Using lower radiance settings than those shown on the screen is not recommended in order to maintain accurate results. It's best to have a ground plane as large as the largest object in the model, or even larger, where there are rooms without obstructions, where ground reflected light can make a difference. But also set the ambient resolution so that the minimum separation for cached radiances, as mean, is kept to no more than 0.16 meters. If using an ambient accuracy of 0.01, this translates into an ambient resolution of no less than half the largest dimension in the model, expressed in meters. An optimal grid size appears to be no more than 0.3 meters, and possibly with a narrow wall offset may be proportional to room dimensions. Overall, the results we have gathered so far indicate that the luminance-based recommendations in EN 17037 may be easier to comply with than the daylight factor-based recommendations. However, we need to continue the analysis for different orientations. But nonetheless, the UK National Annex criteria are easier to meet than those in the main standard, as expected. Next, we need to complete the daylight autonomy calculations for the study on the calculation grid, as well as the fourth study on the weather data set for climate-based daylight modeling. And this is the plan we have set up for this. We are planning to use weather files from Energy Plus, CIPSI, and Time at One building for a selection of UK locations and calculate the luminance inside 4 rooms facing each main orientation, as well as horizontal and vertical luminances on the roof of the building. If time allows, we are also hoping to undertake additional luminance calculations using rcontrib, which is a different algorithm to rtrace that turns off ambient caching and interpolation, to calculate daylight coefficients faster before embarking on completing the main study for other room types, including, we hope, school classrooms. We hope to have our findings and guidance available by early next year. I would like to end my presentation by thanking my colleagues, Paul Littlefair and Gerald Howlett, as well as my former colleague, Stephanie King, for their valuable advice and input into the project, including a lot of time-consuming daylight calculations. Thank you for your attention.
All right. Thank you, Cosmin, for your important work and sharing the research with us. I think what it illuminated was how important the details are in these simulations, especially with regards to threshold-based daylight standards and then, therefore, compliance-based standards, whether a space meets or does not meet. Clearly, it's very important, so thank you.